Hey guys, so just like every class, even though this is a video, we're going to start with the problem of the day. So once it loads, let's do the Lewis dot diagrams of these three elements. You should pause the video at this point, and when you are finished, let's check with the people around you, and if it matches up with two other of your classmates, you probably did it right. So pause the video at this point. If you're back with me, today what we're going to be looking at are two exceptions to how we've been drawing these subatomic particles. So the protons, we know, always need to be the same. They can't change, because if they change, we have a different element. But the electrons and the neutrons can sometimes have some nuances. We're going to first look at ions, which are situations where the protons do not match the electrons. And then we're going to look at situations called isotopes. These are when the neutrons don't necessarily match up with what's on the periodic table. Let's first look at an atom of sodium. Normally, sodium has 2 electrons in that first electron energy level, 8 electrons in that second one, and 1 valence electron in that outer ring. Sometimes atoms can give or take away their electrons in order to reach a happy octet, as I'll call it. Atoms love to have 8 electrons in that outer ring. That's their happy place. So, sodium has the ability to get rid of that final electron, that valence electron, but that comes with a situation. We have 11 protons in the nucleus, but we have 10 electrons circling around that nucleus. The protons and the neutrons don't match up. This is what an ion is. The charge on this sodium atom is a positive charge. This is because we took away an electron. So we have 11 protons and 10 electrons. 10 of these electrons are canceling out the positive charge of the protons. But we have that 1 proton left over. So that means we have a positive charge. I would like to re-emphasize, in order for an atom to get a positive charge, we can never add a proton. If we were to add a proton here, we would no longer have sodium. We would instead have magnesium. So in order to get a charge on an atom, we could only add or take away electrons. In this case, we took away. If we ever have more protons than electrons, we have a positive charge. If we have more electrons than protons, we have a negative charge. And here's an example of that situation. If we have a chlorine atom that was given an extra electron in order to reach that happy octet I talked about, it would have a -1 charge. Note though, in the notation here, similar to the sodium ion, when it's just a 1, so +1 or -1, we don't write the number. But here, in this example, where we have oxygen, it has a -1 charge here, but it doesn't have that happy octet. Ions don't necessarily have to reach that happy octet of 8 in the outer ring. Here, oxygen has 7, and this ion is possible. This happy octet is not always the rule, and many of the problems I'll be giving you will be atoms that are not reaching this happy octet. This happy octet is just something that we're going to be looking forward to when we start looking at bonding. But let's look at an oxygen that does reach this happy octet. It would have a -2 charge because it gained 2 electrons in that outer ring. Note though, on the notation, it's not -2, it's 2-. This is the notation we're going to be using for negative ions or positive ions that have values greater than 1. Cations are positively charged ions. This is like the sodium we saw before, the Na+. Anions are negatively charged ions like the Cl-, the O-, or the O2-. And I have some nifty ways in order for us to remember the cations versus the anions, because this is new vocabulary and it might be a little hard to remember. Yes, we do always have our cheat sheets on quizzes and exams, but committing some stuff to rote memory can be useful at times. So here, the cations have that T inside, which looks like a plus, which could be useful to remember that it's positive, whereas anions, in the second letter, have the N like negative. If you don't like this, I have a punny way of remembering it as well. Cation has the word cat in it, so it is positive, because cats have paws. So, moving forward, let's do a practice problem here with a phosphorus 2- ion. So let's draw both the abbreviated Bohr and the Lewis dot diagram for this. Let's pause the video at this time. So, if we check with our peers, we should have gotten essentially the exact form of a Lewis dot diagram that phosphorus would normally have, except with 2 extra electrons, and likewise the Bohr diagram should be the same, but with just 2 extra electrons. Let's now look at isotopes. Ions were situations where the electrons didn't match the protons. Now we're looking at situations where different atoms of the same element have different number of neutrons. So here is an example of a hydrogen atom. As we can see, and if we look on the periodic table, a classic hydrogen atom has 1 proton, 1 electron, and no neutrons because it has an atomic mass of 1. This is called light hydrogen, sometimes called protium. If we look at a different isotope of hydrogen, namely deuterium, it has a mass of 2. It has a neutron that protium didn't have. Deuterium isn't as common as protium. We only see it in about 0.01% of hydrogen cases. That's why the atomic mass on the periodic table is much, much, much closer to 1. It's 1.008, because almost all of the time it has a mass of 1. But there are those cases where it doesn't. There is even another isotope of hydrogen. This is called tritium, and this has a mass of 3, and it's highly radioactive, used many times in scientific lab and experiments for radioactive detection. So, as you can see in all 3 of these examples, they have the same number of electrons, same number of protons. The only thing that's different are the number of neutrons. That's the only thing different in an isotope. Here is how you'd see me commonly label these different isotopes. The number on top is the new atomic mass. So whereas normally hydrogen has an atomic mass of 1, an atomic number of 1, this isotope of hydrogen has an atomic mass of 2, and still retains that atomic number of 1 because it's still the element hydrogen, and that number can't change. Likewise over here, atomic mass of 3, an atomic number of 1. I understand that this is contrary to how it's labeled on the periodic table. On the periodic table, the atomic mass is on the bottom, and the atomic number is on top. We have to, I guess, deal with the fact that it's slightly reversed. It's completely reversed in this situation. But it should be easy to identify because the larger number is always the atomic mass, and that will be on top. Here we have helium, which normally has an atomic mass of 4 and an atomic number of 2. Isotopes can also exist in situations where they lose neutrons, as we see here with helium-3. Helium normally has that 4, but it lost one and has 3 neutrons instead. So it has 2 protons and 2 neutrons normally, an atomic mass of 4. But it has that atomic mass of 3 in this isotope, leaving it then with 1 neutron. So now, let's take these two ideas and bring them together for this problem over here. Let's draw an abbreviated Bohr diagram and Lewis dot diagram of this ion of an isotope. We have a mass, atomic mass of 15, 7 protons, which is normal for nitrogen, and it has a 2- charge. So, let's pause the video, consult with our classmates around us, and let's see if we get matching answers. I'll kind of briefly explain the answer to this problem after you pause the video. For this Bohr diagram of nitrogen 2- with an atomic mass of 15, we should first start out with the classic nitrogen atom. It should be the same as the classic nitrogen Bohr model, except now we have an extra neutron. We have 8 neutrons rather than 7. And now, looking at the electrons on the outside, we should be adding 2 extra electrons than normal. So we should have 2 in the inner ring, and instead of having 5 on the outer ring, which nitrogen would normally have, we should have 7. Looking at the Lewis dot diagram, the fact that this is 15-7 nitrogen does not affect the Lewis dot diagram. We should write the 15-7 on the side, but the actual dots in the Lewis dot diagram only care about the 2-. So, we should have 7 dots around the outside of the Lewis dot diagram. We should have 2 on the right, 2 on top, 2 on the left, and 1 on the bottom. Let's check if this matches up with your peers, and we'll talk about this in class on Monday, so don't worry if there's still some confusions. We'll be working on the Bohr worksheet number 2 for homework, but don't worry if you have some confusions. I may move the due date for that to another time. But let's work on that in class, and let's have it ready by Monday, and we'll talk about it then. Thanks, guys.